Karan requested that I should at least cover decent trees. A complex tree I am as it's also part of decent tree, so I will be mainly covering decent tree and random forest. That will be more detailed actually in this part only. So this is because biologically motivated machine learning techniques means it includes some of the things which are already covered in some of the previous talks. So still I will touch upon actually artificial neural network and evolutionary algorithms like genetic algorithm, genetic programming. Some touch with simulated annealing also. Swarm intelligence I will not cover in this talk. Then exactly how we can apply these things in physiological systems. So let us start. So already you have gone through Dr. Jain's in previous talk actually yesterday. So you have already seen some part of it at least. So cardiovascular models. I will come back to this thing again actually at the end, but I will just give introduction and why we need. So as you see, the cardiovascular system comprises of a lot of vessels around a lot of organs. So they have different, different characteristics. So actually, we often represent this thing as like RC network, RCL, actually LCR networks. But L is actually relatively late, in fact, less used. It increases complexity, and except for some parts, there is less application of this inductance part. So if you remember in the first talk of the short course, Professor Patra already informed why these inductance is required. If we have sudden change in blood flow, so then mass effect of these blood cells will come into play. So this inductance and capacitance is basically actually the compliance of the vessels. So how much it can adapt, okay, how much it can hold that blood volume, and the resistance E is obviously it's clearly understood that your vessel and different constrictions will give some restrictions to the flow. That will be your resistance, and there will be obviously some energy sources, which is actually muscular forces. They will give the energy, and that will create those blood volume. Blood flow will start. That will be analogous to current, and that's why actually these cardiovascular system can be easily converted into RC networks, RCL networks. So why electrical circuits actually preferred? Because they are much simple to work with. But we should not forget actually what are those physical relations between those resistance, capacitance, inductance, and those active energy sources in that circuit. So this is basically cardiovascular model. So as you can see, there are a lot of complexity. So so I hope you can see my mouse pointer. I'm not seeing how to show other types of pointers. So Karan, can you see my mouse pointer?
Yes, sir, we can see that.
Okay. Okay. So we will. I will work within that way. So in this one actually, so if we have some kind of diseases, so some of these nominal values will start to change. So your resistance, capacitance, and inductance, they have some nominal values. So some of them, and also energy source. It has some sort of voltage source you can think about, or like current source some cases. So they have their nominal values. So if we have some diseases, they will start to change. So if we can find these model parameters in both cases, when it is normal and when it is abnormal, then by the basis of these parametric values, of these resistance values, capacitance values, how much it is changing, we can find out how much is the disease. So severity and localization. So actually, where is the disease? So I actually, and for doing that thing, actually, how to generate these models? So how to find out these parameter values? So much of our this internal system, actually internal physiological system, is type of black box. So actually, in most cases, what we can actually what we can sense is actually some of the output variables, and those are the physiological signals, which have been already talked about in the first talk by Professor Patra. So, so those signals, from those signals, actually we have to model or just find out all these values, nominal values, and if we can actually disease values also, because disease values will be compared. So as you can see, and still this RC network is not comprising of all those complexities. As you can see, some cases like coronary vessel, that will be for coronary flow, that is supplying to that heart itself. So blood being supplied to every part of the body, but there is a small portion, uh, it's only 5%, right? 5% of your total blood circulation is only into your coronary, I means coronary artery part. So that is very small compared to the rest of the blood circulation, but it is very, very critical because it is controlling work of the blood flow. So this is basically just like that heart itself is self-motivated type of thing. Okay, self-activated. So that part is not shown here. So there are in that way a lot of other complexities inside which is not shown. So your detailed circuit will be very big, and normal normal modeling, system modeling things may not work well, and uh, and that's why in fact in these cases machine learning will be often indispensable. So similarly, actually, yeah, for say respiratory model, so it is basically a counterpart of the of this cardiovascular system. So instead of blood flow, now there is airflow, and this is actually more significant in these COVID-19 time, right? So there his lungs is getting affected by this COVID-19 virus. So so in this case, actually, we'll be having a clear path, and from that air path, actually, there will be some part will be a dead part of it. There will be no change. So it is in this front part mainly. Then in fact there are some part which is collapsible. Then then there is the actual lungs where we have alveoli. So in the alveoli there are two things are happening. One is actually that that air is coming in. Uh, I mean, as lung actually squeezes, and at that situation, actually, I mean, almost most part of of the air or air mixture is actually thrown out, okay, exhaled. And after that, when it expands, it is creating some sort of vacuum type, I mean, some sort of pressure difference. And and your air will be coming in. So and in this case, actually, what is happening? So for this airflow, there will be also some resistances. Okay, and some resistance, and that volume can change for lungs because of its the large elasticity part. So it will be having a larger capacitance value. Okay, uh, and in this case, inductance is almost never used. Okay, because air particles has very low mass, so and that's why actually change of even if we have large changes in this airflow due to some disease or something, often still your that change of mass effect, inertia effect will be much smaller. So we do not represent that inertial part. So it is basically RC network. I will not go into details of this RC network because I know some part of it has been uh, already discussed in actually one of the earlier talk by Professor Paul. So in this case also there will be a lot of complexity. That is not shown. All these complexities are also not shown in this model. If we have disease, there will be more complexity. So in this COVID thing, what will happen actually? This lung part, some of these alveoli will be filled in with the virus that will create spasm, or like what I will say, some sort of sap, or like some sort of liquid. Okay, so lungs cannot handle liquid. Okay, so when it squeezes, it cannot squeeze out the liquid part. Okay, so it has less capability of dragging the air or like inhaling the air. If we have less inhalation, means there will be less oxygen available, and that oxygen is required in your in this entire body. That's why we suffer. So in this lungs also there is actually another part which is actually your that gas mixture, gas diffusion. Okay, so so in that walls of the alveoli there will be that oxygen will come out of the air and enter to the blood, and carbon dioxide will be actually transferred back up from the blood to the air and will be exhaled. So all these different parts will be having different models. As for here, actually, it is in this case actually top part is basically airflow part, and bottom part mainly for your gas mixture. Okay, so this is pneumatic part, pneumatic hydraulic part. Okay, so in this case also there will be a lot of complexities which a general system modeling may not be able to handle, and that's why we need machine learning type of thing. Let us now start with basic classification. So machine learning is actually one type of classifier. I mean, machine learning is basically one tool which can be used for classification also. As Karan suggested that I will at least give some of these basic ideas. So I will start with this. I mean, with this basic of the classification. So. So we have basically, as we have told, although this thing, all these illustrations are taken from one very standard book, actually, pattern classification by Judah and Hart. So as it is not directly related with with this physiological system thing, but I mean, I will explain how it is related. Okay, so basically, if we have one system, we sense it by some signals, physiological signals. So what are those physiological signals? Say actually ECG, electrocardiograms, right? So it is basically electrical functionality, activity inside your uh, inside the cardiac system. Cardiac means the heart system. Heart, as it is pumping, actually those electrical activities are captured in the ECG. And similarly, we have blood pressure signals. Similarly, we have, as you have heard, those brain signals. Brain also have those activations, and that is sensed by actually EEG, electroencephalogram. So for myotic things, actually muscles, we have actually EMG, electromyograms. So in that way, there are a lot of signals. So basically, we sense those signals. Some of them will be uh, uh, temporal continuous time signals, just like ECG, EEG, EMG type of things, and some may be periodic, just like blood pressure. Often, I mean, if it is externally taken from sphygmomanometers, so it will be actually a discrete type of things. We take, I means discrete in time, not in value, discrete in time. So we will be having some of those type of signals also. So these signals are actually raw data, which we may call as like signal space, input space. So there are two ways to now visualize. I mean, now analyze this data. Okay, so one way is classical way, which was done earlier, which is by finding out features or like its signatures. So by which we can try to identify uh, type of the signal. Is it a normal ECG or abnormal ECG? Something like that. So those are basically features. So as simple features, if we have one signal, if we take its mean value, it is one feature. Okay, if we take its standard deviation value, if we take its envelope and then find out that sum of its like peak to peak values, so those are its features. So now those features, how can they help to classify? So in this case we have two features. So in the if you now look into the first plot, so it is one of the feature being, now we have generated a histogram. Okay, so in this case, this is particularly actually one case with say two of these I mean, and in this particular example we uh, actually have two classes. Okay, class 1 and class 2. So this is class 1, which is represented by the black histogram, and this is actually red one, which is basically your second class. Okay, red histogram. So if they were completely separated, okay, if they were by chance, if they are completely separated, actually we are good with it. That itself, histogram classifier, by if we now find out mean of it, that will explain. But even without mean of it, if we can find out that some level of this feature value which can completely disjointly distinguish these two classes, there is no error. Okay, I will explain what is error, classification error. Okay, so but in this case, unfortunately, there is a quite big number of, I mean, big amount of like overlap. Okay, so anything in this part, I have no knowledge actually whether we can, uh, whether it is of this class 1 or of this class 2. Okay, so now say we take now another feature, and that one has little bit less overlap. In this case, we can sort of find out valley points. So it has two distinct modes, distinct peaks, and we have one clear valley point. Although there will be some classification error due to there is some overlap, but that valley point, if we have distinct valley point, that will be best what we can do if we have only that feature. So how to find out that valley point? You have probably heard about the name of Otsu's threshold. I know Otsu's threshold is most known for image processing people, but it can be in exactly same way it can be used for in like any dimension. Okay, so if you have also multi-dimension also we can apply. Also for single dimension also we can apply. So I'm not going into details of the mathematics how to find it out, but it basically judges how distinct is your peaks and how distinct is your value between them. So they are basically interrelated. If we have distinct peaks, means value also will be distinct probably. So in this way, we will be if we can find out in fact such separation point by this threshold value, that will be our classification surface. Or this is also called classification surface in this particular case. But still, they are not fully categorizing because we are identifying actually we are utilizing only single feature. If we now actually but now plot this thing instead of single dimension, if we do a scatter plot. Scatter plot means every data point is plotted as one dot in the feature space. So feature space may be two-dimensional. In this case, we have two features. That's why feature space is two-dimensional. So we can have multi-dimensional also. So if we have so if we have multi-dimensional, in that case, that visualization will be difficult, but we can visualize up to probably a 3-dimension. So we can select best 3 features. So I will discuss also later that how to select best features, and that will and in this case, as we are looking for classification, so as for feature space classification, so we will be preferring on those features which can act better separate out two classes. Okay, so in this scatter plot, if you now see, so now it is looking relatively better in this two-dimensional feature space. So all the black dots are of one class, and these red dots are of like another class. Okay, so so what happens? So now actually, if we can so now classification surface we can now decide. So instead of in this case this was one single value, but as this is now two-dimensional, so your classification surface will be one dimension less. Okay, so you should remember that at least one dimension less. So generally it will be actually just one dimension less. So in this case it was actually one-dimensional plot. So your classification surface was 0 dimension. So it was only single value. In this case, we have feature dimension is actually 2. That's why our our classification surface will be basically one line, which is actually order 1 polynomial, right? Order 1 polynomial. So, but as you can see, some of these points, if we just make it, sorry. So, so you can see some of these small red dots are there in this side, and some of these black dots are in the other side. So those are actually classification errors. So let me shortly define what is classification error. So in this case, so if we now classify by this line, say, in this case, this part, the black part, which is being misclassified as this red part, is basically false negative. If we take this thing as positive case, this thing as negative case, so this is basically false positive. I mean false negative. Okay. So in this same way, this red part here will be carrying false positive part. Although this is from this negative class, it is being classified as positive part. So it is actually false positive. So in this case also we have false positive, false negative. So actually and these false positive and false negative, and in this case this part actually dark this part black part in this side, this area will be actually carrying your true positive. Okay, so this is false positive and this is true positive. This is sorry, this is true positive. This is false negative. This is false positive. This is true negative. So with this false positive, false negative, true negative, we can adequately define accuracy and sensitivity, specificity type of things. I hope you already know these things, and uh, so I will not go into details of those things. Otherwise, I cannot complete even the part of this talk. So now, to improve that accuracy, that is the classification accuracy. I mean, the classification error. So to reduce that classification error or to increase your classification accuracy, we can modify our classification surface. So instead of single order, I mean, instead of single order polynomial, we can now have a multi-order polynomial. So actually polynomial of multiple orders. So if we can define in this way, actually one of the classification surface as drawn by this curved line, so all these points are correctly classified. So obviously, in just looking into it, it will be looking like that it is better classification surface. But what we call is basically overfitting. So I will explain. So actually, this line is being generated. The classification surface is being generated on the basis of what we have seen so far. So these are generally called a training set. So in the machine learning, we'll be again talking into this training set. So a training set is that data set for which we know the levels. As we know the levels, we can actually generate these classification surface. And on that basis, if we have some point, I mean, so now if we have some test set, so which this classifier have not seen so far during the training, during generation of this classification surface. So now it will try to classify on the basis of this line of classification surface. So if we have this type of a complex surface, there is good chance that if we have say some point, I know this is very small looking, so let me increase its size. Let me just increase its size. Yeah, so if you see this thing, there is actually one small question mark, and that question mark is for the test set. So if that thing comes by this classification surface, it will look like that it is basically red class. But if you see nearby values, nearby samples in that scatter plot, it is more crowded by these dark, I mean, these black dots. So actually, we will probably like to see that thing as from the black class. So it means it may be basically from the black class, but it is being classified as red class due to your complexity of the classification surface. It means your classification surface can represent or is representing the test set, I mean training set very well, but not the test set. And that is called overfitting. So it is extensively fitting training data, but it cannot keep that generalization, okay, genericness. So that is actually one of the definition how to choose actually which classifier to use. So I will come back to that thing again later. Okay. So let us now again go to this presentation thing. Yeah. So now better will be if we can little bit improve by actually increasing polynomial order, but not that much. So that will be something like this probably. Okay, so how to decide that thing? There are a lot of thumb rules, a lot of matrices. So we will discuss little bit of those things under other classifiers later. Okay. So now a selecting classifier, already we have mentioned little bit there. So that if we have more complexity, it is probably will try to overfit the training data or like data which you have already seen. So there is one very old principle which is called minimum description length. So it is short form is MDL. So MDL means that generally, if we have to generalize some classification, it should be the simplest which can work for the training set. Simplest form. So because simplest in the sense that it is not required that your training set error, classification error for the training set goes to 0. If it goes to 0, that is probably overfitting. There is very in fact high chance of being overfitted. But it should generalize for that a test set part which it has not seen so far. So if we have lower order classification surface, that will be probably better for generalization. So these testing error are called actually generalization errors. So so now actually, so there are two ways. So maybe there are some features which are not that much informative. Okay, so say in this case, actually, or sometime, so actually, if there are some features which are not that informative, we can remove them or modify them, or we can do some feature mapping into higher order or lower dimension or the higher dimension. So say in this case, so in this particular data, actually, what is happening if we have like one linear classifier, we can actually adequately separate it out. But if we have this type of like feature space where your scatter plots are like that, there are two classes which are intermixed. So actually, either you can do what, that you can find out this line. In this case, this is circle, so it is basically second order polynomial. So either we can have on second order polynomial, we can find out, or we can plot this, in fact map this thing into some higher space where it will be linearly separable. Okay, so I hope you understand this one, that if we so our classifier, I mean that order will like to have simplification, but these mapping, we can have some nonlinear function. Okay, obviously we would not like that to be too much of complexity, but so in this case, phi is your basically that nonlinear mapping function. Sorry. Okay, so this is nonlinear mapping function which is mapping it back, and in this space we can linearly separate. So this is called kernel mapping. So this is kernel function. So this is yeah, often used in many of these of kernel learning type of things, Gabor kernels, or and there was some old neural networks, actually something uh, was called Canon's the map, the neural network. So in those ones, actually, it was mapped to higher space. So, and also we can have sometimes for the lower space. We uh, can synthesize some feature with some weighted or parametric function of multiple features. Okay, in that way. So now, how do we know that which data sets are good for classification, whether we can really apply classification or not? There is one very well-established method which is called Fisher Linear Discriminant Analysis, FDA or LDA. In this case, actually, if we have two classes, even if we do not know its class levels, okay, if we do not know class levels, it means we know there are two classes, but we do not know what are those classes names or the class levels. So they are specifically fit for unsupervised learning. We will discuss it also. So unsupervised, so in this case, like, there is no output level class known. So in those cases, so if we have something like this, okay, if we have this type of scatter plot, so if we know there may be three classes, so we can try to find out three clusters. Okay, so clustering you have heard. So clusters, how do we know that it should be three clusters or four clusters or something like that? So that is depending on this Fisher discriminant analysis if we do incrementally. So if we start with single class. So if we take this is as like single class and just find out its mean, cluster mean, and its variance value, standard deviation. Okay, then we try to fit it into two classes. So again, if we take two classes such a way that their means are most different and most distant. I mean, means are different and they have cohesiveness. Means their individual standard deviations for individual clusters are small. Small compared to your that case when all of these points were considered to be of same class. Okay, so if we can reduce variance of standard deviation value. Okay, so in this way, so in this case, if we can reduce, that means it is better to have two clusters. And if we now break that thing further into three classes, just like in this particular case. So in this particular case, they have tried with three clusters. And they are more cohesive. If we have three clusters, they will be probably more cohesive. So they have their individual mean values, they have their individual standard deviation values. So on the basis of their standard deviation values, and if we consider that thing into a single class or two class, actually how it is improving, that is actually done by this Fisher discriminant analysis. How much discrimination can be done if you do this type of clustering. So this is actually some part of also K-means clustering which we have heard. So we generally give this number of clusters K, right? How many clusters I would like to have from it. So or we can do these things adaptively. Okay, so we start with the single cluster, we just go on. So if we now try to further break it down, so linear discriminant analysis will restrict, because in this case they are very well correlated. So if we now take this one as like some separate classes, they will have they are pretty in this case in fact close to this one also, maybe close to this. So say this class, I mean, we get this sample if we have single class now. So in this case, this is pretty close to this cluster and this cluster. So there will be be some ambiguity. So if we have different class, that will create more ambiguity because standard deviation will be high sometimes. If we have now this 3, if we try to put it into a single class, it will have actually a higher standard deviation. So in this way, actually, we our goal is to increase its the distances between the clusters and decrease standard deviations of those clusters. I mean intra-clusters. Intra-cluster variance should decrease and inter-cluster differences or variances should increase. So mean value, the distances between means, the cluster means should be increased. So that is basically done in this FDA, LDA things. Okay, this thing is also same as for like in this case, if we now do one of this x1 square, x2 square, we can have one linear classifier so that we can spread it out. So let us now go to error surface. So this is basically starting with machine learning. We are now entering. So so error means actually so in that previous case, if you remember, in this case there were some cases which were actually misclassified. So if we now take a summation of those errors, how much in how many cases we have done this error and by how much. So these distances from this classified surface gives by how much we have done this error. Okay, so we can define some in fact some metric so which will be defining your that classification error. So that error, if we now represent as a function of complexity of that classification surface or your classifier, so that forms your error surface. So in this one we have shown this thing in single dimension. Okay. So in this single dimension, so your error surface, like error, if we now in fact take that thing as like mean of square errors or like root mean square RMS error, something like that. So it will be one single scalar value that will be varying. So and they may have different variations. So so when we start by taking our some assumption of the classifier, that okay, I will start with say second order polynomial classifier. So it will start from some point here in this error surface, somewhere it will start from. Then on the basis of how much error we have done, we can improve. So say in this earlier case, say if we have started this line in this way, so there was some error. So on that basis, we can actually start to change slope of this line, and we can orient back so that there is error is reduced. So this changing slope, okay. So your line has y equal to mx plus c. So c is your that intercept, m is your slope. So m and c both we can change actually, and such a way that our error will be reduced. So this MC space is basically your those parameters. We classify hyperparameters which we change some way, either manually or automatically. So in this way, error will start to change, and error will change. Yeah. So in this case, this is your say a candidate classifier which will start to move either this way or that way. So actually, while moving, so how it will move? So if we have some error, so I will try to find out those parameters. So partial derivative of the error with respect to some of the parameters. So if we have say m and c for the linear case, So we will, if your E is your that value of the error that is plotted here, so we will find out a dou E by dou M, and that is actually how much error is varying due to change of this M, and that if we take negative of it, so if it is giving positive error, so if your uh, if we now change this M value, it will so that your error will be reduced. Okay, so if we have larger error, we will try to reduce, so it will be a negative of that partial derivative. I think you have heard this thing in some previous talk on that optimization. So I will not detail there. So our next selection of the parameter will be basically dependent on those those partial derivatives. That is called gradient descent algorithm. So and if we multiply that thing with one factor which is called learning rate, how fast we want to. So if we are moving in this line, say, okay, so in this line, say, so in this line, so it is gradually reducing. So it will go farther. So error is reducing means we are in the right track. So after some time, it will reach some point, and and that is one valley point, right? So you can visualize this thing also in that Otsu's thing which we have discussed earlier also. So in this case, so now if we now move further, it is going above, right? So it means in this case error is increasing. So it will again come back. So as error is increasing, so that negative sign will will just oppose your movement in that direction. It will move in this in downhill way, and it will come back to this point. So this is actually minima, one of the minima of this error curve. But as you can see, this is not the global minima. It is local minima. So it is stuck in here. So actually our global minima may be somewhere here. So by the way, this error surface is only for showing the thing, because often your classification surface, though those parameter values can change from minus infinity to plus infinity for every parameter maybe. So there are infinite number of classifiers. So we cannot define the entire classification surface in any way. This is only for visualization, or like only for illustration purpose. Okay. So in this way we have local minima, global minima, local maxima, global maxima. So if our classification target is to reducing error, that will be actually looking for global minima. It may just stop at these local minima also, but our goal is for global minima. If our classification target is to increase accuracy, so we will try to achieve maxima, so a global maxima of the accuracy. But we may actually may start with local maxima also in those cases. So now how to and that will be more visually appealing if we see some cases like this. So say we are considering single dimensional feature space, or a single dimensional error space, sorry. So our that complexity of the classification surface, instead of say n, if we now instead of say 1, so in this case this was our feature like that, the feature space, the parameter space of the classifier, this is your error, right? So if we now increase our number of parameters of the classifier, so it may happen in your say a 3D surface, it may happen that in this curve, it has reached minima. But that is not minima if we now, if we project these things onto this plane, it is not minima. It is actually maxima in this particular case. So it is not a global minima at all. So this type of point is called saddle point. So this thing came from the saddles we have seen for the horses, right? So it should now, after reaching here, it should now move down in this path, not in this way, but it should move in this way, in this other switch space. So how to know these things? So so I will in this case I will just introduce actually one concept which I have mentioned in my first slide. It's called simulated annealing. So this is basically it's not exactly biologically motivated, but actually we can think in that way also, that uh, in metals when we try to make it strong, okay, we repeatedly heat it up and cool it down. Okay, that is called annealing. So simulated annealing or in fact, Boltzmann's machine that follows that thing actually. So it tries to do some perturbation. So it will increase its error instead of if if that error reached here, so it will uh, uh, it explicitly give some perturbation so that that error increases. So if it by chance reaches up to this point, then if we now start, so it may now actually go to actually global minimum. In this case, if it was struck here, if we now increase its temperature or that error, and if we can if we can reach up to actually up to this point, then if we now do gradient descent, then it will try to actually follow this path, not this path. So it will come out of global minimum. So so simulated annealing performs in that way. So I will not go into details. So now uh, Karan suggested me to do some at least some description of decision tree classifier, which is like one of the earliest machine learning technique probably, and also simplest, and still it is often actually very good one. So machine learning actually, so I mean before going to this thing, I should mention about supervised and supervised learning, right? So uh, error and all those things we are mainly computing with the best of that. If we know the levels, if we know the class, if we know the class, that will guide us. So that will supervise us. So that is called supervised algorithms. So if there is machine learning, so machine learning is basically what? It is basically adapting based on the data. It is nothing like it is nothing like God gifted. Okay. So let me tell you that even for human actually, machine learning is happening based on actually what we are seeing. So from the baby, the baby will be seeing something on the basis of that thing actually he's or her parents will be telling that this is told, this is actually this is actually this object, this is actually that object, and on that basis uh, uh, in fact that baby will start to learn. Okay, so he will learn actually he is my father, he is my mother, in that way. So in this way actually he is learning. So exactly same way, unless we give some ideas, often it is difficult. So this is actually supervised learning. So from the data, we are learning what is what. So on that basis, if we now see actually one unseen object, we will try to classify. So this is so adaptively. Okay, so if we have one very few data first, we will learn something. Then if we see few more data, actually our learning perception will change, right? So exactly same way, at supervised learning, maybe incrementally learn also. And also there are something which is called unsupervised learning, when there is no classes attached to the data. So still, as we have seen, that if we do not know the class, if we know they are clustered, so at least we can tell they are different objects. They are different objects. So, and then later stage, maybe in the next stage it will be defined, or some prior knowledge will come, or some post-processing knowledge will come, that this cluster is male, this cluster is female, this is water, this is milk, by the color, or something like that. So this will come later, right? So in that way. So in this way we have supervised learning, unsupervised learning. So I will not go into details because I hope some of this already has been covered, or you can go to any standard book. So I will start with, so let me check what is the time, how much, oh my God. Okay, so I will speed up a little now. I have taken too much time in the earlier ones. So now decision tree classifier, which is not exactly biologically motivated, but still it is very interesting that it is rule based. So what do we do if we go to one supermarket, if we try to buy something, and if we have multiple options? So we check for a couple of its attributes. So these are actually features which we have told earlier. Features, attributes are actually interchangeably used often. So these attributes are basically, actually at first we will check those things. So they maybe the brand, maybe our prior ideas, prior knowledge of using that particular product, and also obviously price. So these are basically attributes. So we now compare that, uh, and on that basis we also try to find out which attribute we should consider first. So there is some kind of a hierarchical uh, rules. So priority of the rule. So which rule we should take. So say we say that at first we should go by equality. So and so in that way, what will happen, that say brand will come first. So we know a couple of brands are good. So rest of these other brands we will not consider for now. Okay, so these brands which we prefer now, that will be at first considered, and on that basis actually after brand, which is our next priority attribute. So say now we say our prior knowledge, I mean prior experience. So out of those brands, now we see that okay, this brand is better, this brand is not. I mean, this brand I have used previously. This has some problems like this. This has some problems like this. So accordingly, we have some more rules that I will classify by that. Then maybe price. So there will be price there. Price will come, and now out of say two brands, which is cheaper, that one we will go for. So now there may be also changing. So say some of the price suddenly changed, some of the brand's price suddenly changed. So we will now go back to my previous priority and traverse some other path. So so this thing is actually rule-based decisions, and this is represented by some tree structure. So now, uh, uh, so they actually basically look like. I am just giving one example, something like this type of thing. So actually, I mean, for food habits, we can find out uh, uh, food habit and some I mean some other habits, some genetic I mean hereditary information. We can find out chance of diabetes of a patient. So say in these cases, actually we have some kind of like hierarchy. Okay, so if we found high glucose, no high. So if it is high, then there is chance of diabetic already. So if we now have checked whether he is already diabetic, so in that case it will be no, will be moderate risk. If we have already diabetic, in this case of which a high risk of diabetic problems. And if we have also low high glucose things, still actually maybe high BP, so like there may be a diabetic family history, and all those things hierarchically actually come down. So in the leaf actually we have some classes or levels. So they either may be isolated levels or maybe some probability values. If we say actually identically that it is risk, so that risk value will be low here, that will be moderate here, that will be high here. And on the basis of different attributes of the data. So this data, most of this data will be available. So on that basis, we can find it out. So if we have this, actual disease tree has been made out of some training data. If we have some supervised data, and from that thing, if we have generated that thing, then only we can classify. So now how to generate the thing? So you should now remember, so each of these are actually attributes. And at every level, we have some set of data. On the basis of these bifurcations, some of these data are now partitioned. So some part of this, and they are in fact disjointly partitioned. Okay, they are mutually exclusive. So they are disjoint sets. So we have some data sets left here, some data sets left here. On that basis, again, we decide high BP, and we further now classify. So and in that way, we actually in this case go up to this thing. These are called leaf nodes. So this is the root of the tree, and all these are actually root branches, and each of them are actually attributes. And there we have some rules we are using. Then on the basis of the rules, we are going by into one of the branch, and actually we are trying to reach the leaf of that decision tree, and either we are knowing exactly which class, or we are getting some probability value of being in one class. So already I am with less time, so I will just go on. So and now actually first option will be how to decide which feature to consider first, which we have already told earlier, right? That out of that supermarket buying that product thing, that which feature we should take, whether brand will come first, or price will come first, or prior experience will come first. So that is decided by preferential order of the feature, which is either we can go by PCA, principal component analysis. It's something a little bit newer way of doing this, but some regular standard way is by information gain. So if we split that thing, how close are we to the leaf? Or like how close we are to the certainty. So what do you mean by certainty? If we have higher probability for one class, and low probability for the other class. Okay, so if we have, say, two classes or one three-class problem, if one of the class has pretty high value, so in that case we say it is almost certain that that class is a valid class. We can go for that class itself. So that is called certainty type of thing. That is your, it means actually you have more knowledge. You have less uncertainty. So this uncertainty can be defined by one term is called entropy, which is from information theory also. It is a thermodynamics. If we have more Brownian motion, we have more entropy type of things. So if we have uncertainty, right? So in this way, that is so in this information theory, this entropy is defined by if we have probability of one class. So X is one of the class, small x, and capital X is basically set of all the classes, all classes. Okay, all the classes. So if we now consider this one of the class small x, so it has some probability value px. So by this term, this is your entropy of that class for that particular data set. So inside one data set, how to find out its individual probability? So by simple statistics. So if we have say 50 data points, and out of that thing, that particular class is happening 15 times, so its probability will be 15 by 50. Okay. So that will be our px. So now actually, if we now have minus px into log 2 px, that will be your entropy for that class. And then if we take summation over all such class entropies, we have HS. H is your entropy term. S is the entire data set. This is your entropy of the entire data for those class, for that type of classification. So if you now take this attribute A, so attribute is your feature. You should remember attribute is your feature. And you have a label. Okay, so which is your classification. So by that thing we can now that if A is given, on that basis if you now try to classify only based on A for that data set. So that will give you entropy for this term. So earlier there was no bifurcation, so that was HS. So now we are trying to bifurcate with respect to the attribute A. So this one will have some entropy also. So this difference is basically information gain. So how much information we are gaining, how much uncertainty we are reducing. This is uncertainty. So how much uncertainty we are reducing. So this gain part is basically defined in this way. So your V by S. So your V is your subpart. So in this case, there are, so V is basically one of the class. S is your total sample size. V is your sample. This thing is number of samples for that particular V class. S is total number of data. So and that is your So that is your this term px, and on that basis, actually now we can find out actually how much is your feature gain. I mean your actually how much is gain of entropy. So there is also one more index is called Gini index, which is basically these probabilities, class-wise probabilities. C is total number of classes, I is for every class now we are taking, and pi square. If we take summation of that thing, that will be is called Gini index, Gini purity. So from that basis also we can also find out entropy. I mean on that basis also you can find out information gain, and on that basis information gain for which class, for which attribute, if we bifurcate, we have most amount of information gained. On that basis, we will be selecting our features. So this is basically learning algorithm of the decision tree. So, at first, historically, it was actually ID3 was first came. Then it was modified into C 4.5, C 5.0. Then some more of the variations. So in these cases, actually, I will little bit explain about this ID3. At least some classification algorithm I should explain in this talk. So how that is being done. So in this case, actually, H's for this for the nodal data. In this node, at first we are finding out for that particular node how many is your positive case, how many is your negative case. So we find out. So now we have three attributes A, B, C. So for now, ABC will be now finding out which one, which one I will select. So I will select that particular attribute for which we have maximum information gain.
Hello.
Yes, some question? Okay.
Hello.
So, on that basis, we will split that thing.
Hello.
And if we split now by either attribute, that will say if we have say three types of values there, so it will give rise to three branches. If we have two values, it will be having two branches. So our goal is that up to when we can go when actually in this individual node there is no more mixture of levels. So mixture of levels is zero. So that means there is zero entropy. There is no uncertainty. So if we have zero uncertainty, we will stop there. Otherwise, we will take some part of the data for which attribute value is 1. Or say in this case, actually, see if you have some other attribute, so if value is A, and for this value A, we have some part of the data. And for that data set, we will now again recursively continue. Subset, recursively continue subsets using remaining attributes. So if we are out of any other attribute, we will stop there. Okay. So if we have continuous, so in this case, we have three possibilities of the values. So it is A, B, and C. So it is called discrete values, discrete variables. If we have continuous values, we can also, either we can use some, we split into disjoint segments by one threshold value TH, and that threshold value can be found also by information gain. So we will actually just one entropy calculation so that you you at least understand some part of it. Excuse me. So in this case, what is happening? So if we so in this case we have outlook weather, temperature, humidity, and wind, and on that basis we will be deciding whether we will play golf or not. This is one very standard. Standard example actually given in Tom Michel's book Artificial Intelligence. In this one actually, so if we are considering that entropy for outlook, okay, so on the basis of outlook, if we try to break out, in that case, what is the entropy value? So how to find out? So we will be at first finding out this individual, so if we have this thing actually only by play, so for this entire data set, how many times so if we have how many data sets? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have all total 14 data set, data points, and out of that we have 1, 2, 3, 4, 5 are no, and rest 9 are actually yes, right? 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Okay. So our probability. So in that case, entropy we can find out now for that entire data set. Yes, by this thing that your the probability of no is 5 by 14, and probability of yes is 4 by 14. I mean 5 by 14, and that is 9 by 14. Okay. So now what happens? Now we will try that if we now break by outlook, how good is that criteria? If we have sunny, how many times we are having yes, how many times we are having no? If we have overcast, how many times we have yes, how many times we have no? And if we have rainy, how many times yes, how many times no? So on that basis, now given outlook is sunny, what is the probability of playing golf out of this data? So that we will find out this way. So in this case, px will be now that term. That so in this case, actually, what is your term? This is 5 out of 5. We have 2 of those. In this case, it is yes. So so at first, actually, sunny versus at things. So actually, it's so what is probability of your class sunny class? Okay, so that is 5. Total 5 out of 14. Okay, and overcast case is 4 by 14, rainy case 5 by 14. Okay, so then for this term we'll be finding out for how many cases we have that probability values will now calculate by this term. Actually earlier we have decided by this this sunny value. Okay, so actually yeah, P play golf outlook is P sunny into, in this case, 2 and 3, this term but now will generate this part. We'll find out that the entropy value from that. And also entropy value for this, entropy value for this one. And that will be summed up for entropy value for all total. And that will, that value, if we now take a difference as we have actually defined earlier, as we have defined earlier in this case, we now actually use this one, we can find out information again. And if we now consider for outlook as well as for temperature, for humidity, for wind, so whichever is giving best best information again, that one we will first select. And on that basis, we will generate our first branching. So our first branching will be generated in that way. And after that, we will be having sub part of the data here, sub part of the data there. On that basis, now with rest of the attribute, we will be now classifying again with exactly same method recursive. I hope you have understood some part of it. I'm not going to details there. So as also Karan suggested, something to be detailed. Oh, I am almost there. Okay, so let me just quickly just go to this random forest at least, because Karan suggested to at least cover some part of it. So so in this decision tree, it suffers from actually overfitting, as we have discussed earlier, overfitting thing. So it suffers from overfitting. So if we have less number of training data, it will try to classify in that way, and it cannot classify other things if we have a new data. So that is corrected by this random forest thing. And random forest means we have many trees, and out of these many trees, they will give their own opinion of classification. Then we'll be doing some voting. So on the voting, actually, whichever class level wins, that will be our final class. So that is basically something like this. Okay, so this is something like we have different trees, but one interesting thing will be they are not considering all the features. So I will now come back at how they are different. So they use something is called Bootstrap aggregation, or like short form is bagging. So we actually we do some random sampling of the data subset with replacement. So this thing is very important, that with replacement part. So when we are sampling, so actually we are taking, say, same number of data. So if we have n number of data, we are again taking n number of data, but with actually we are randomly sampling n times, but with replacement. So there may be uh, multiple copies of same data set, and there may be some data sample which is not at all represented in your training data. So this is one. Then and then we will train actually one of the tree by that bootstrap. Sorry, this is called bootstrap sampling. So actually, with that bootstrap sampling, will be a training at one of the tree, and we will actually do this for so many trees, such trees. In this case, actually, I have taken capital B as number of trees. So actually, and how to find out testing errors? So still, it is actually taking overfitting probably. So now testing error will be coming out of some of these data set are not represented after this random sampling with replacement. So and those are called out of bag data, SB dash, SB prime. Or we can do cross validation, which I will not discuss probably. It has been discussed earlier by other speakers probably. So actually, as those out of bag data has not been used for training, so we can use that thing for testing purpose. So and in this is called bagging concept. Okay. Then we have also do another and that is represented by this one. Actually, we can also find out how much it is error for those out of a bag data. Okay, so and from this out of bag data we can also actually find out its variance also, and that will be a measure of actually how much varying are those individual classification trees. So now also there is actually one more randomness here, that is actually random subset of the features. So instead of all the features, we'll be taking one small subset of that feature, and that is as by thumb rule, it is generally taken square root of total number of features, or sometimes a by that number by 3 also sometimes. So then actually out of those, we randomly selecting that number of features, and then we are generating that tree. So that means there will be a different trees, and they will be having different data sets on which they are training. So there is complete randomness. So it is now becoming generic. Okay. So that will reduce that generalization error. So if we have missing data, that also can be handled by this random or systematic case first. Then actually we correct that value gradually based on feature importance. That variable, that feature importance can be found out from those out of bag errors for different trees. I cannot go into details of those things because of less time. And there is also one variation which is called extra trees, where there is no bootstrapping entire data set is used, but top-down splitting, random cut points. So there is no randomization here. It may be used in that way also. So this thing, then after that we have different trees with same number of features, but a different set of features. So they may classify differently for same instance. then it will be doing actually one majority voting and give you a final class. So I have told about feature importance. We can find out missing data handling. We can also do some kind of unsupervised learning with the help of clustering there. And on that basis, so actually we have subsamples. On the basis of that thing, we have different trees. Then actually now we have these initial root nodes. Then all these split nodes are there, and after this split node, we have all these training nodes are there, and actually where we are actually getting actual class. And if we have different classes, we'll be doing majority voting. Okay, that will be random forest decision. You should remember that that random forest, although it is a little bit older thing, but still it is a very powerful machine learning technique, and it can. It is still, even in this age of deep learning, still often it is it is found to be the best one. So I had a lot of things left, but I will stop here. So do you have any questions?
So thanks for a nice presentation.
Ma'am, thank you.
Yeah, so I know actually, I know that I have said biologically motivated one, but I could not enter there. I hope audience could understood at least these things.
So one of the questions have been raised by the participants, that can random forest be applied to regression?
Can random forest be used for regression?
Yes, sir.
Yes, it can be used for regression also. So in that case, actually regression case, what will happen? Those output variables or output classes will not be one single class type of things or like discrete values. It will be basically real number, continuous values. So if we have that type of way, we can use regression analysis also, regression trees. So in this way, we have regression trees. So if we have discrete ones, that we just call that thing classification tree. If it is actually having those real numbers actually at your leaf node, it is called regression trees.
Okay, sir. And another question has come up: which ML algorithm is best for conditional switching applications?
For conditional
Switching application.
let me check this thing.
Yeah, the questions you can see in the chat window, sir.
Yes, I am seeing that thing. Just hold on.
Yes, sir.
So let me stop scary. Just stop presenting. Stop presenting and make my video over. Yes. So which ML algorithm is best for conditional switching application? So the conditional switching application, I will say actually decision tree type of things may be very good. So as there is conditional things are there, so conditions means rules. So decision tree will be better option. Not unless we have pretty complexity, I will go for decision trees, not random forest.
Okay. Audience, if any, is there any other question?
No, sir.
Okay, thank you for your participation.
Hello.
Dr. Ghosh, thanks a lot for your talk. It was a nice presentation. We are recording the sessions and we shall be sharing the recordings with the participants after the completion of the course.
Yeah, that is okay. But Karan, I will just in this recording itself, I would like to give one disclaimer. The disclaimer is that I have not in my presentation. It is very prepared in like very short notice. So I could not. I know Karan gave me actually enough time, but I did not give enough time to that thing. So anyway, I could not give those citations from where I have taken those all the pictures. Most of them are online pictures. So I
Okay.
will suggest nobody share the presentation among others. You can just view it, but do not share this.
Sir, but will it be fine that if we can share the presentation with me after this session? Because I was thinking to share the presentation with the participants.
Then that is okay. But as long as you keep this last disclaimer which I have told right now.
Okay,
Okay, you
sir.
should keep this one also recording that I am
Yeah, that is
confessing that
fine. That is fine.
yes, I had less time to put those things.
Yeah, it is fine,
So
sir. That is the disclaimer.
yeah,
In fact, you can include this disclaimer while sharing your presentation also.
yes. Okay, so I will also in this one I know there is very less time here. I will just try to add one small thing. As this is physiological, I will show one. I will share for just few minutes one thing. I would like to share this thing for those who are trying to apply physiology. I mean, trying to apply machine learning for physiological signals and systems.
Okay, sir.
Actually, one very cautionary word. So that's what I was I was about to come at the end of my presentation, but you could at least share this part.
Sure, sir.
ফায়ারবালিং ওইটা তাহলে একটা আনবে। আর তোমার এই যে দুটো বই অর্ডার দিয়েছি 808 টাকা আসবে,
Hello,
পরের সপ্তাহের মধ্যে আসবে।
Costa, please mute your microphone.
হ্যাঁ
Costa, please mute your
দুটো
microphone.
পাঠিয়েছি।
Yeah, so I will
ওই
just
যে 2 পাতা 3 পাতা করে আছে। আচ্ছা আচ্ছা,
Sir, sorry for this.
পরের সপ্তাহ।
so
ঠিক আছে।
so I cannot find that exact publication I can send to current letter, but it says that why deep learning, specifically deep learning, they are talking about specifically deep learning, even for machine learning also, why we should not blindly use for physiological systems, why they are not being trusted by clinical people. So I would like to mention that thing at least, that why. That is, as our deep learning, machine learning things take that thing almost like a black box. Okay, we take signals, we find out some features, and actually we try to classify. So it often does not match with the exact thought process, which is so actually, which is going on inside the clinician's mind. So actually, like, what is coming out recently, clinicians prefer something is called representational learning or explainability. So machine learning or deep learning should have some kind of explainability. Explainability means it should explain some of those hidden states, actually, which Professor Patra mentioned in his very first talk. So those hidden states, at least some part of it should be visible. So say in those in the RC networks, we have a lot of R values, C values, inductance values, the energy values. So if we can have one deep learning or machine learning technique, which at first estimate those R values or C values, then it is explaining that by those R values or C values, actually we are classifying this is actually this type of disease. In that case, probably clinicians will be more happy, as those R values, C values have a much better physiological meaning than those ultimate classes of like CAD patient, normal patient, valvular disease patient. So they before coming to that thing, there must be something representation of the model. So I think that's why these online course was very good, that that it is highlighting actually models of the systems, not the signals directly. So I will like to just, I mean, just like to give the piece of advice. If you are going for applying machine learning or deep learning in your physiological systems, and I mean, you should not directly go for classification. If you can come up with a method which can find those representational models, say RC models type of things, then going for actual classification of the disease, that will be more clinically trusted. Okay, thank you very much.
So thanks a lot for the presentation. So let us close the session. So audience, please be back by 1:50 p.m. We have another session scheduled at 2 p.m. So it would be a talk by Dr. Dilip. It's again on PC-enabled SVM classification. So see you all then. So Dr. Ghosh, it was great to have you here.
Yes, hi Karan.
Hello, sir. It was a nice presentation. It's great to have you here at MIPS 2020. So looking forward to have you as a speaker in future, just such kind of conferences or these seminars.
Okay, Karan. Thank you very much. Thank you. Bye bye.
Thank you, sir. Have a nice day.